So thank you for being here. Also thank you, Hilton, for being my host. I would like to say that what I'm going to talk about, has some parallels in the research that is being done here at ENS, has some connections to optomechanics, done in Pierre-François Coadon's group, and also in Gabriel Ete's group with levitated NVs. So has many connection points to activities that are going on here. I will talk about this levitated system. This is a 100 nanometer particle. Here it's actually a diamond. Gabriel, this is the only time when we trap diamond. It's the nicest picture of all. So this is being held here by the forces of light. It's an optical tweezer. And what we try to do is to control the dynamics of the system. Especially we would like to make this system to behave according to the laws of quantum mechanics, to somehow investigate the transition from the classical world into the quantum world. By the way, I encourage you to interrupt me with questions or comments. I take no offense. Yeah. So, oh, come on. Yes, I would like to start with acknowledging the people behind this. This is my group at ETH working on this. Yeah, no? Yeah, I go here. No, you see a little bit the pointer. Martin Frimmer is a senior person in my group, and he takes most of the credit for what I'm going to tell you. Then, there's a whole row of postdocs and graduate students. These are former students, and Jaya, Andre, Eric, and Masi, they just left in the last 3 months. Now, Johannes, Maria Luisa, they're about to graduate, and Tita is about to leave the group. So you see, I have a problem, so that's why, if you're interested in what I'm saying, please get in touch with me. I also would like to highlight here Louisiane, because she comes from here. She did her PhD in Sylvain Gigon's group, and is now a postdoc in my group. Then I would also like to acknowledge the groups with whom we are collaborating. This is the group of Romain Quidon at ETH, then the group of Oriol Romero-Izard at Innsbruck, Markus Aspelmeier in Vienna, Tracy also in Innsbruck, and Carlos moved very recently to the TU Vienna. So this control of microscopic objects, in vacuum, this is what we call today levitodynamics. It's the levitation control of microscopic objects in vacuum. And there are many things that you can do with levitated objects. I would like to emphasize here the length scale. So we're not talking, levitation of big macroscopic things like trains, and we're not talking about atomic systems. So it's this intermediate mesoscopic range that we're interested about. And you can approach questions, non-equilibrium physics, in sensing, material science. I will focus in this talk on questions motivated by quantum science. In particular, this is what I would like to talk about. We would like, to place this object into 2 locations at once, simply speaking. We would like to see quantum interference. And this is just, a symbolic kind of perspective. We basically want to do a Young's double slit experiment with a particle of the size of 100 nanometers. This has about 10 to the 12, 10 to the 13 mass units, atomic mass units. Now, if we go back in history and look at the history here, of doing these interference measurements with massive objects, we start here with the electron. Later, there were the experiments done with neutrons and also with atoms. Then this is more or less the work done by a group in Austria at the University of Vienna by Markus Arndt. He went from fullerenes to organic molecules, and here are even proteins today. So this effort is going, you know, from the bottom up. We're trying to come from the top down and bridge here, okay, a few orders of magnitude in terms of mass units. And now, what does this experiment entail? We first have to generate a well-defined state. And for us, this well-defined state is the quantum ground state, the motional quantum ground state. So this object has internal degrees of freedom, like phonons and so on, but they're highly decoupled, okay, from the center of mass motion. So I will only talk about the center of mass degrees of freedom, okay? So translations. We also can rotate these objects or liberate them. I will not talk about this. I will talk just about translational degrees of freedom. So this object is being held in space, and because it's being held, there's a potential, okay, that it's subject to. And in this potential, okay, it has, okay, some confinement and some trap stiffness that ultimately dictates, okay, what this ground state is. So once we ground state cooled this, and this is in a well-prepared state, then we would like to expand the wave function. The ground state wave function is 10 picometers, okay, but the physical size is 100 nanometers. So just intuitively speaking, if the wave function is smaller than the physical size, it's a particle. And what we try to do here is to exploit some kind of a wave nature, which is associated with the wave function. So in order for the particle to go through two slits, we have to expand this wave function so that the wave function interacts with both slits. Okay, so the first step after ground state cooling is wave function expansion. And then this double slit basically stands mathematically for a nonlinear interaction. You can just imagine this is a double well potential, for example. And that generates this quantum interference out there, which ultimately, in order to generate it, we have to always measure the particle and then repeat the same experiment under identical conditions to build up that statistics. Okay? So this is what we're trying to do, and this is a European project under the name of Q-Extreme with the collaborating groups that I introduced before. So I will tell you where we stand. Okay, we are standing about here. Okay, and whether we at the end will manage to do this, this not only depends on our skills, but also, you know, whether certain theories are right or wrong. Okay, there are theories that forbid, okay, this experiment to happen. Okay, some collapse theories. I will not talk about this. It's outside my comfort zone. But if we can really realize this experiment, we can exclude some theoretical predictions. Not only this, let me go back. If we have this interference pattern, we can also investigate how this interference pattern interacts with external forces. And one of them is obviously gravity. So we would have, because this object falls and evolves under the influence of gravity, and ultimately the interaction with gravity has an influence on this interference pattern. There are also questions, okay, in the context of dark matter. Again, all this is outside of my comfort zone, okay, but I know that there are groups of people who get excited about this. For us, it's just a challenge. Can we get there or can we not get there? So this is the outline of my presentation. I give you a short introduction. Then I will talk about active feedback cooling, then our effort in state expansion. Then I will also talk a little bit about passive feedback cooling, and then give you an outlook of where we stand and what other interesting questions there are in this context. Okay, so our history starts with these pioneering experiments done by Art Ashkin, who laid the foundation, okay, of, I would say, lots of modern AMO physics. In 1969, he already demonstrated the trapping of microparticles both in gas and in solution. And he writes in this paper that the extension to vacuum would be very interesting, since then any motions are frictionless. In a follow-up paper, he thought, no, even in vacuum you must have some friction. So then he actually already 2-3 years later, okay, he realized there is something like a vacuum or radiation damping, which is related to ultimately the same effects we encounter in atomic physics. But anyway, so if we think about these optical tweezers that he invented, and that are widely used also in the biological context, then usually a particle is held here in the focus of a focused laser beam by this gradient force. And as highlighted here, this is a conservative force. Now I would like to just illustrate what's happening here with a skateboarder. So this particle enters here a potential, like the skateboarder, a half pipe. And the reason why this particle gets trapped is because they're also non-conservative forces, but they're not optical in nature. Okay? Here, these non-conservative forces are just a Stokes drag force because we have a medium around, and this medium dissipates energy. Okay, so this is the same as, you know, having here on this half pipe, okay, some friction, which ultimately, you know, allows the skateboarder to be trapped. But if there was no friction, the skateboarder would appear here with the same velocity as he entered. So now we're in vacuum and there is no friction, although there is some residual, but not enough, okay? Another question is, how do we generate artificially this friction in order to hold this skateboarder in place? And the recipe is very easy. We basically, in time, modulate the potential. So imagine the skateboarder arrived at the bottom of the potential well, and then we just crank up the potential. Okay? Then obviously the skateboarder has not enough energy to escape anymore. And then you can think a little bit further. It's like, okay, now he's still bouncing in here. Well, you could actually modulate this potential in some clever way in order to dissipate the energy. Okay, so the message here is, by temporal modulation of a potential, we can generate non-conservative forces and thereby do work on a mechanical system. So we need both. We need a conservative force to hold a particle in place, and we need a non-conservative force in order to cool or accelerate the particle. Now, this is one of the pioneering papers, okay, that nicely explained the physics for me. This is just a harmonic oscillator of a cantilever. Here we have some thermal forces of, you know, stochastic nature. And then here, this is a feedback force, and Khaled here in this paper says the essence of cooling is based on the fact that the optically induced forces acting on the lever are delayed with respect to its motion. Okay, so if we go back, okay, these forces, okay, that we apply here to the skateboard are delayed with respect to its dynamics, and the delay generates a frictional force. Now, this delay we can do in two ways. One way is an active feedback. So we monitor, okay, the particle, what it's doing in time, and then we have a clever logic that acts back on the degrees of freedom of the optical field. So we basically, you know, modulating the potential here by having a certain recipe. You can do it passively in the context of cavity optomechanics, where the light scattered by the particle is rerouted back to the particle and exerts with some delay a radiation pressure force. And the delay, again, is accomplished by detuning the cavity from exact resonance, for example. This is called resolved sideband cooling. I will first talk about the active feedback. Okay? But before I do this, I would like to establish the terminology. So if we have this particle that is now trapped and it oscillates, scattered light reaches our detector. Okay? And this scattered light ultimately gives us a signature of the motion of the particle. Okay, so you see this oscillates, the envelope is slightly changing because there's still a residual gas. the gas molecules colliding, and they're changing here the oscillation amplitude. If we now Fourier transform this time trace and take the absolute square of it, okay, this is what we call then the power spectral density. This is what it looks like. It's a Lorentzian, okay? A slowly varying, oscillating function as a Lorentzian, as a Fourier spectrum. So this is the raw data, okay? And if we want to calculate what is the mean energy contained in this oscillation, well, because this is, you know, a harmonic oscillator that exchanges a kinetic with potential energy on a periodic basis, we know that this energy, this mean energy, can just be expressed in terms of the mean square displacement. So in principle, already just this time data can be used, okay, to extract the energy or derive the energy. This is the mass and this is the oscillation frequency, which is very well known. But we can go now through the Fourier space. We can now look at this Lorentzian. In this Lorentzian, we have two contributions. We have a background, which is shot noise, which we subtract. On top of this shot noise, we have the Lorentzian. And the area underneath the Lorentzian, if we integrate this Lorentzian, okay, that gives us the mean square displacement. That's more or less the definition of a power spectral density. So we can just take the area under this Lorentzian, we integrate it, okay, and we have the energy. So just remember for the later part of the talk, if we see peaks, the area under the peaks tells you what the energy is in this mode. Now this energy can be expressed in different units. You can use calories, joules, whatever. In this business, it's customary to express it in terms of a temperature. So we equate this, okay? And this has nothing to do with equipartition, and so we just, okay, express this energy in terms of a center of mass temperature, okay, by dividing by the Boltzmann constant. What is also customary is to express this energy in dimensionless units, okay, and an effective occupation number. Assuming, okay, this beast would be a quantum oscillator, then we know, okay, these energy states are separated by one phonon energy, h bar omega 0. And so we take this energy, we divide by h bar omega 0, and we have n. And that tells us an effective occupation number, okay? So I will be either using temperature or n, okay, in the context of this talk. Both of them relate to energy. Okay, now just a few things about the cooling dynamics. I have here my oscillator. Okay, now I use y, okay, as my coordinate. This is a harmonic oscillator, has the eigenfrequency omega 0, has some damping gamma, and here's some fluctuating terms that drive the oscillator. It's a Langevin equation. Now, the feedback gain in vacuum is dominated, the damping in high vacuum, when there is no gas, no solution, is dominated by the feedback that we apply to the system. So we have a clever feedback that we adjust such, okay, that the energy of the system becomes less and less. And that accounts to a damping constant. So this is our feedback gain. But then we have always things that drive our system. And in vacuum, this is the recoil of photons. We're measuring the system. And in order to measure the system, we have to throw photons at it. And every photon that collides imparts a momentum recoil. Okay? So ultimately, these photon recoil kicks, they have a power spectral density here. And now, if we just take this equation and calculate what is the mean energy in this oscillator, we arrive at this first order differential equation for the mean energy. And you see it has both terms. It has the cooling term and it has a heating term. And now in steady state, okay, the mean energy is not changing anymore. Oh, because we are in a steady state. So in the steady state, cooling equals heating. Okay? And this is shown here. So once we activate our feedback loop, we reach a steady state. And this steady state is just given by the ratio of heating to cooling. Okay? So it's not only a question of how well you can cool the system, but it's also a question of how much you heat the system. Okay? It's the balance of the two that ultimately determines what is the steady state energy or steady state center of mass temperature. I mean, ultimately, this is nothing else than your car. No? This is the brake pedal, this is the gas pedal. You press both, okay, and the car will equilibrate at a certain velocity. Okay? So same business here. Okay, so let me talk about how we do this with active feedback. This goes back, okay, to a row of very nice experiments done with optomechanical systems, okay. Here, one of the very first one was done in the group of Pierre-François here. Then we also have similar things done with microspheres and even with atoms. And we're doing similar stuff. We started with a system that can be explained by this marble in a ball. Okay, so this marble oscillates in this ball, and now our job is to make sure through a feedback that this marble, comes to rest. And how we do this, okay, we first observe what the marble is doing, okay? Then we process this information, okay? And then we act back on the system. So if I give you this system with the marble oscillating back and forth and I say, bring it to rest, you're automatically going to do something like this. And you do not need to understand the physics, okay? Because as you do this, your brain optimizes, okay? Ultimately, your objective is to bring it to rest. And you will figure out at one point what is the right frequency and what is the right phase, okay? I've done this with my children, and they couldn't care less about physics, okay? But they got it right, okay? So ultimately, if you cook this up, this amounts to a parametric feedback. Okay? We're basically going to oscillate here, this dish, at twice the oscillation frequency. And with just the right phase in order to counteract the motion. Okay, so it's a parametric cooling mechanism. And with this parametric cooling mechanism, we want from this big Lorentzian, all the way down to this Lorentzian. And remember, I told you, okay, the area underneath the Lorentzian is the energy, okay? And this is on a logarithmic scale, so there is much, much more energy here than down here. So expressed in phonons, or occupation number, here we are at 50 phonons, okay? Pretty cold, but it's not a quantum ground state. Good. Now we couldn't get better, okay, for a long time, till we learned something, okay, from control theory. This is a paper by Romain Guidon's group. It says for linear observable system, the optical control law is known as the linear quadratic regulator and is widely utilized in larger mechanical systems. It guarantees that a dynamical system will minimize its energy in the fastest way possible. Okay, I like this paragraph, okay, because you can read an entire book about control theory, but they are not able to say it so compact, okay. So we realized, okay, our feedback is not the optimal control strategy. So we went to something called cold damping, okay, going back to the roots, okay, this is the paper basically done by Pierre-François. So our particle is here, and now the force is not optical anymore. The force that we apply is electrostatic in nature. So you see we have here two plates. We apply a voltage and the particle is charged, and we can add charges, okay, to this particle through a plasma. So you see here individual charges hopping on and off. So we can nicely control how many charges are on this particle. So what do? We have our laser system. We send this on the particle. Ultimately there is a trap. This is still optical. The optical trap holds the particle. But the photons that are scattered are collected, and this is the measurement. So the optical field does two things, okay? It generates the potential for the trap, and it is used for the measurement. Okay. And then the measurement here is converted into a voltage, and this voltage is applied here across these electrodes to generate an electrostatic force. And as indicated up here, okay, basically we take that this force that is applied is proportional to the velocity of the particle. Okay. So let us look at the equation of motion. This time I'm using Z. We have two noise terms here. First of all, this is, the noise, the random noise generated with, by the recoil of the photons. We call this the back action noise, okay? Because we want to measure the particle, okay, and we disturb it. It's a back action. And then we have this term here. You see, this is our feedback term, because here we're measuring Z, okay? And here we take the time derivative, and that's what we feed back. So this is the feedback force. But our detector not only gives us the position, it also has shot noise, okay? And this is Zn. This is an imprecision noise. So we have two sorts of noise. We have the back action, and we have the imprecision, two noise terms. And both of these noise terms, they have their power spectral densities, okay? It's usually white noise across, okay, the region of interest. So now we can Fourier transform this whole thing, okay, and express this, okay, again in terms of power spectral densities, and we get this equation. So the mean energy of our mechanical system is dictated by two terms. One is the back action that drives it, and the other one is the imprecision, okay, associated with the noise on the detector. And now in our system, we can measure all these parameters independently. Okay, so you see that there are two noise terms, okay, and there is a feedback. And I give you here just an example. Let me go back. So for example, we can just at one point switch on the feedback. Okay, and then we observe, okay, the mean energy of the oscillator and nicely goes down. And with this exponential, we can extract the damping rate. And so we have this gamma feedback nicely determined. We can also say, hey, now that we reach this low temperature, we can just switch off the feedback. Well, what will happen is there's still photons that are hitting it and that heat the system. So the system will reheat under the influence of the light field. And so here we have basically the recoil heating rate. Okay. So basically all these parameters before we can nicely measure in our system, and that I would like to just say here, typically we are adding with our light field about 10,000 phonons per second. That's how strong this heating is. What is very important is also to know where the information is going. So imagine a photon scatters at the particle, and a scattering means that it carries away information. And you want to use this information. I only told you, it imparts a back action, which is something that we want to avoid, but ultimately it also generated a measurement, and we have to collect this measurement. And the question is, where do these photons go, and which photons carry the maximum information? So that was a mathematical exercise that my student Felix did, and he came up with these information radiation patterns. This is not just a Rayleigh scattering pattern. The Rayleigh scattering pattern tells you where the photons go, but they don't tell you where the information about the motion went. Okay? So then, once we analyzed these patterns, then we exactly knew where we have to detect. And that made a big change. No, now it gave up. How come? Yeah, that's how far I got. Yeah, I think the batteries are gone. There's also no light anymore. On. Yeah, okay, so I will get rid of this. Good. So knowing these information patterns, first of all, knowing the balancing of imprecision and back action allowed us ultimately to shrink this Lorentzian to zero. Okay, and if we just there's other things, okay? There's something like noise squashing because you're feeding back noise and you're still driving the system. I spare you the details. But believe me, just looking, okay, underneath these areas, and as shown here on the left-hand side, okay, we can go here to an occupation number of 0.65, and in the jargon, okay, of this business, okay, whatever is less than 1 is ground state. Okay, so we reached here the quantum ground state. I also would like to say this was a work done in parallel with Markus Aspelmeyer's group, but with in independent work. So I would also like to tell you how to measure energy better than just integrating the Lorentzian. Because once you're down here, integrating noise is very tricky, okay? And deriving then a number of 0.65 by doing this, nobody believes you, okay? So you have to be a little bit smarter, and I would like to talk about sidebands. So if you have light hitting an oscillating mirror, then the reflected light will be phase modulated, no? So if we have just e to the I kx, okay, going this direction, okay, and now x is being modulated here with x0 cosine omega 0 t, and now you expand this entire thing, okay, and then you get not only a contribution at the, well, sorry, there is still a minus I omega t, okay, this guy, but here we have another frequency, omega 0, so 2 time dependencies, and that generates, okay, these sidebands. And they're not only 2 sidebands, there are multiple sidebands, but they become very small, okay? So we have 2 sidebands just generated through phase modulation. And this is shown here. It just turns out that this is the classical world, okay? But we know that a quantum oscillator, okay, has a ground state energy. And just because, okay, this oscillator cannot have 0 energy, you build in a certain asymmetry into the system, and it just says that one of the sidebands is slightly higher than the other, okay? So we have like a Stokes sideband and an anti-Stokes sideband, and there's a slight little difference. Okay, so in our system, what we do is the following. So we have this oscillating particle in the light field, and with a lens, we're collecting the scattered light. And again, in addition to just the spectrum given by this laser field, we have here a phase modulation on the scattered field according to this factor, so that generates sidebands. And in the next step, we would like to shift these sidebands into the frequency regime where our photodetectors respond, okay? And we do this with a local oscillator. So you see up here, okay, we have delta omega. This is just a frequency shifted field. And if we then look at our spectrum, it looks like that. So at positive frequencies, where we usually measure, okay, we have a Stokes and an anti-Stokes sideband. And what is very nice, okay, they are different by exactly 1 quantum, 1 phonon. And we know, okay, first of all, we know Planck's constant pretty well, and we know our oscillation frequency also pretty well. Okay, so we know what this difference is in terms of energy. And therefore, we can use this as a ruler. We can just take this difference and step it down and calculating how many n's we have. Okay? So this becomes a very accurate method, okay, of extracting the energy from a system, and this is called sideband thermometry. If we do the sideband thermometry with our levitated nanoparticle, this is the sideband asymmetry we measure, and we extract an occupation of 0.66. And then we have 2 quadratures, okay? We have a phase and amplitude quadrature of the scattered light. We can correlate those, and from this correlation, we can also extract an occupation number as 0.64. So we have 3 independent measurements, and from these 3 independent measurements, we get more or less the same number, which makes us believe that we reached the quantum ground state. Good, so here's a summary of this little section. What we've done is actually verified this formula. What do we have? We measure a power spectral density. Let's go back, okay. Here, this is a power spectral density. This Lorentzian, this is what we measure. This is this yellow highlighted thing, okay. Now, this has 2 parts. One is the imprecision, and the imprecision is given by some prefactors, okay? So 0-point fluctuations, okay, or the variance of the 0-point fluctuations, okay, is given there, okay? And you see there's a gamma measurement. What does that mean? Okay, these are the photons that are scattered and that we measure. It's not all the photons, okay? Just a certain number of photons that's scattered. This is what we measure. We call this the measurement rate. Now we have this other term here. First of all, we have the forces, right, acting on our system, and our system, okay, having a transfer function, these forces are translated into a displacement. Okay, and we have the response function of a harmonic oscillator, and the forces that act on it, this is radiation pressure shot noise, you see, has again this 0-point fluctuation square, okay, from the 0 point, but it has a different gamma. It's a gamma tot. This is the total number of photons that scatter at the particle, no matter whether we detect them or not. Okay? Every photon that scatters at the particle imparts a momentum recoil. So there are two different gammas, okay, and the ratio of these two gammas is what we call the measurement rate. So we are not able to detect all the photons, okay? Our measurement rate is only 0.24, and that's why we can only cool to 0.65 and not to 0. Okay? If this measurement rate was 1, we would be able, theoretically, to cool our oscillator to n equals 0 exactly. Good. I will skip through this and now go to state expansion. I hope I convinced you that we can do ground state cooling. We can improve a little bit, okay, to n equals 0.5, 0.4, and so on, get gradually better. And that just means we're improving our state purity more and more. Okay, now our state purity is, I think, something like 60%. Again, okay, improving this measurement efficiency, we bring the state purity up. So we have now a well-defined state, okay, of that mechanical system. Now we need to expand it. And how do we do this? Before I go into the details, if you just take this 10 picometer, okay, wave function, and you just let it evolve, okay? Let's say there's no gravity. You just release it in outer space. Within 10 milliseconds, okay, that wave function will grow to 100 nanometers. Okay? It's just a Schrödinger equation with an initial condition of a wave packet, and then you basically look at what time, okay, it expanded. Okay, after 10 milliseconds, it's already expanded to the size of the particle. So, the problem is the following. If we release it, okay, well, it will drop, okay? You can handle this a little bit, but it generates a little bit an engineering overhead because you drop it and you have to catch it down there and so on. It becomes a little bit difficult. So we don't want to drop it. We want that it is quasi-dropped. We drop it, but it's still held by a very shallow potential that just counteracts gravity, okay? And this is this blue line there. You see this here? This is our optical trap in which we ground state cooled the particle. And now we're building around, okay, this optical trap, a shallower trap. And now you could think, okay, let's just defocus the laser beam. The problem is the following. During that free evolution, we don't want any measurement. But an optical trap has photons and they scatter and this amounts to a measurement, okay? So if you let it expand in an optical potential, okay, you basically decohere the state pretty fast. So we have to let this particle expand, okay, or evolve in a what we call a dark potential, and this is in a Paul trap. So similar to the experiments that are done in Gabriel's group with diamonds. So we have here an optical trap. This is red, okay, this is the particle. And here in between the lenses, we have this thing down here with 4 electrodes. And with these 4 electrodes, we apply alternating kind of voltages to basically generate a potential for this charged particle. And that is ultimately this blue potential here. Okay, so now we have 2 potentials, a stiffer one and a weaker one. The weaker one is an RF potential and doesn't measure. So our protocol is the following. We first ground state cool this particle, and this is our phase space distribution. Okay, so it's a nice Gaussian kind of distribution in the ground state. This is position, this is momentum. Then we switch the optical trap off. And what will happen is, now we suddenly have a different trap stiffness, okay? Which means along the momentum coordinate, we have an elongation. But in the position, we still have the same coordinates, no? Because the particle cannot instantaneously jump, okay? It's still at the same position. Okay, so now you see that we have like a squeeze state here, elongated along the momentum coordinate. Now this being a harmonic oscillator, it periodically exchanges, okay, potential and kinetic energy, which amounts to a rotation, okay, in this phase space. So this distribution will rotate with time with the frequency omega pole, which is the trap stiffness of the pole trap. Good. So now we allow this to just rotate exactly a quarter period till it's elongated along the x-axis, and then we switch back to the optical trap. Okay? And then we have this situation here. Good. Now, this is a protocol we just stole from the literature. That's where the references are. The final squeezing that you can achieve, okay, is given here just by the ratio of trap stiffnesses. And so this is what we just did very recently. Here we have our initial Gaussian state. And now doing this protocol here, you know, you have to switch stuff off and on and so on. It's a little bit difficult, but at the very end, we get a nicely squeezed state. So this sounds very great, but what I did is I cheated, okay? This is not the quantum ground state here. This is a thermal state, okay? So we're in the process now of pushing this towards the quantum ground state and doing, okay, this wave function expansion. That's where we stand. Good. Now, I would like to skip through this just for the sake of time, that we have enough time to discuss. Here I would just say that we can do exactly the same with a cavity. When we started with this, we didn't know which strategy is the better, the active feedback or the passive feedback with the cavity. The active is easier. But we still couldn't let go of the cavity. Okay, that's why we continued with the cavity as well. And I would just like to tell you, okay, if we do all this, okay, then here with these side bands in the cavity, we can also get to occupation numbers less than 1. Here we cooled 2 degrees of freedom, 2 translational axes simultaneously. Okay, so the X motion and the Y motion are both cooled to the ground state. In order to do this squeeze or this ground state cooling, you have to fulfill some more conditions. So if you had one particle, okay, you basically have to fulfill this resolved sideband condition. Now this has to be fulfilled for both modes. But in addition, okay, this is now a 3-mode system. X, Y, and the cavity. Okay, and there's a dark mode. And the coupling to the dark mode has to be suppressed, and that generates an extra condition down there. And now, since I learned this morning, okay, about the nice experiments done in Jakob Reichel's group, I would just like to say this is what we're working on now. We're putting more than one particle into the cavity, and we're looking how these particles interact with each other, not by direct interaction, but by communicating to the cavity mode. So both of these particles coupled to the cavity mode. And what you see is, as we change the laser power on one of these particles, okay, Some modes, they cross, like here, okay? Some others, okay, they have an avoided crossing, a strong coupled situation, and we end up with hybridized modes. This is a very complicated system, and without the guidance of our theoretical friends, we would have no chance to understand what's happening here. The goal at the end, okay, I mean, I started, okay, with my pitch, make out of one particle two, no? Here we would like to make out of two particles one. Okay, so to entangle the motional degrees of freedom of these two particles. Good. So, outlook. Where do we stand? We are still working on wave function expansion. I think we're still going to work for 2 years on this, because you have to expand by 4 orders of magnitude. We are confident we can do 2, but 4 orders of magnitude is a big challenge. And then the next big challenge is to generate a nonlinear interaction, which we don't have in our system. These are harmonic oscillators, and the classical dynamics is exactly the same as the quantum dynamics. So what we have to have, okay, is this nonlinearity in our system to generate a non-Gaussian state. So basically, we need a double slit. Okay, and let's say in optomechanics, people, what they do, they couple their mechanical system to a qubit very often. The qubit is the nonlinearity. Okay? We don't have in this frequency regime a qubit. Okay? And now you can think of many strategies. You can think about some pulsed sequences. You can also think about building potentials that are non-harmonic. There's a switching from a harmonic potential to like a quartic potential. So there are many ideas, but I think it becomes exponentially hard as we get there, and I still hope that on the way there, we will encounter the magic qubit, okay, that will do the job for us. If you have ideas how to introduce a non-linearity here, I'd be very, very grateful. Okay, so with this, I would like to say that at ETH, we are working not only on superpositions. This is more or less what I talked about today. We also work on entanglement in cavities. I touched on this very shortly. I didn't talk about rotations. You can, if you have elongated particles, you can liberate them, okay? But you can also rotate them, okay? And you can couple these rotations to the translations. And then, you know, these particles have also internal degrees of freedom. They have phonons. And with Brillouin scattering, you can address these phonons, and that's also what we are working on. And now I promised to Martin Frimmer, okay, that I advertise this conference, okay, which also has a nice presence, okay, from here. Gabriel, I see you there among the speakers. So we try here to bring different communities together, okay? The atomic physics community with our levitodynamics community. Then like Stefan Village and other people, there are people doing levitation of molecular systems. So the bottom line is many people levitate for different reasons and bringing different communities together. Hopefully, okay, that generates some synergy. So if you're interested in this, keep this in mind. This is in October. And then again, okay, people leaving me. I need new PhD students and postdocs. So thanks for your attention.